6.4, modeling data with a curve of best fit. Now yesterday we talked about a line of best fit. Today we're going to talk about a curve of best fit. So a curve of best fit is a curve that best approximates the trend on a scatter plot. So when we're dealing with a quadratic, we're going to use the function quadreg, just like yesterday we used Linwretch. And for cubics, we're going to use cubic reg. Now these are our two curvy functions that we're going to be dealing with. The constant function is a line, linear is a line, but the quadratics and cubics, they have curve in it. Now a lot of questions will have what type of curve it is right into it, but we're going to do a little bit of analysis here in this video, just in case you get a question where it's like, use the curve that approximates this data best. So this is going to be tough because what I'm going to do is I'm going to type in all of these with you. Okay, I'm going to suffer through it just like you're going to suffer through it. My suggestion is take out your calculator and punch in the values as I am punching them into, just so that you can get a sense of how long these types of questions take. Actually, because if I just have all the data inputted, it makes it look really easy, and also it's just good practice with the keystrokes. So example number 1, using technology to solve a quadratic problem. Audrey is interested in how speed plays a role in car accidents. This is why I love Applied, because actually there are they put a lot of time and effort in the textbook to take examples that are from real life. There aren't any pieces of made up data, or I know for certain that they've done lots of research to make sure things are quite accurate. So yeah, thanks grade 12 Applied textbook, you're great. She knows that there is a relationship between the speed of the car and the distance needed to stop. She has found the following experimental data on a reputable website, and she would like to write a summary for the graduation class website. So here's a whole bunch of stuff. Now, if we wanted it to go on forever, it would actually go speed, oh, wait, and then this down, and then this down. So we have to read it carefully. So this is the speed in kilometers per hour. So we're going to be punching in a lot of data. So this is our independent. Indep. And we're going to put this in list 1. This is our dependent. This is going to go in L2. All right, y'all ready for this? It's going to be a bit of a doozer. So I'm going to go into my calculator, and I am going to hit on. Oh, look, there's the answer. I did it before just to make sure it's all cool. So this is going to make me cry. Clear list. Second, L1, enter. Done. So everything in L1 is done. Stat, clear list, second, L2, done. So when I go into my table here, I have no data, which again makes me cry because all of this was in there before. So let's do this, because question number 1 is plot the data on a scatter plot. Determine the equation of the quadratic regression that models this data. So we're going to do this. 90, 36, 65, 56. And as I'm typing them in, I'm double checking that my fingers haven't hit the wrong button. 65, 24, 35, 55, 81. And if you're really fast, you can watch this video in like 1.5 speed or 2 to keep up. 83, 25, 77, 32, 76. Ooh, going to the next one right here. 38, 92, oh, 92, 22, 31, 50, 52, 33, 27, 33, 32, 47, 95, 24, 23, 79, 83, 50, 48, 45, 81, 42, no, 81, yeah, oh yeah, right there, 42. Boop, boop, boop. 31, 38, 29, 77, 76, 55, 79, 23, and 49. Give yourself a big old pat on the back because that was a lot to type in. Okay, y'all ready for this? This one has decimals in it. Whew! Okay, so we are going to start right here. 94.4, 17, 49.2, 50.3, 43.1, 10.9, 14.2, 57.3, 76.5, 100.3, 9.1, 10, 77.8. Don't fall asleep. 14.9, 67.3. Now we're going to go up here. 21, 111, 5.6, 16.8, 40, 51.2, 15.9, 7.4, 20.7, 17.9, 41.9, 105.2, 6.7, 6.9, 63.6. Gonna go up here. 130.4, 29.1, 37, 20.7, 86, 20.6, 14, 21, 11, 112.3, 84, ooh, 84, oh no, 84.1, good thing I was checking as I was typing it in, 35.3, you've probably noticed maybe a mistake that I typed in, hopefully not, 81.8, 6.2, da 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 da, and oh no! Wait a minute, no problem. I noticed that 77 has 1. So what I'm going to do is I'm just going to go from 77, which is right here, because you'll notice that I would have to type in 35. So all I'm going to do is scroll back up and go back from my mistake. So 112.3, enter. Just going to make sure the one above it is cool. Oh no! My mistake is up further. I wonder where it is. So right now what I'm doing is I'm just checking through all my numbers here. So I have 77. That's wrong too. So 55. 35. 55, looking good. 76. So 81, yep. 83 is 100, yep. 25 is 9.1, yep. Ah, shoot. So what I've done here is I've only typed in 125. I should have typed in 2 25s. So I'm going to insert something here. All I did was again second insert. So second and then insert. So I inserted a new cell. So I'm going to type in 25 here, and what should happen is I should be good all the way down to the bottom. So now when I'm checking my values here, so say 105, 105 is attached with 95. Good. Okay, so then this one is actually just 11. Perfect. You know what? That was really great, because then you can see how we can worm our way out of mistakes. I could say I did that on purpose, but that would be a lie. All right. So we have everything typed in. I punched in my 35 here, and so hopefully I didn't do any more typing mistakes. So let's see what the answer is here. So I'm going to go Stat, Calc, and I'm going to go down to Quadreg. Not Quartreg, but Quadreg. So I'm going to hit Enter, and I'm going to go L1, comma, L2, vars, yvars. Enter, enter, enter. Oh, I forgot my little comma here. So Quadreg, L1, L2, and commas between, vars, yvars, enter, enter, enter. Should go like that. It's thinking real hard. And look at that. That is the right answer. Now we're noticing our r-squared value. It is close to 1. It's 0.9. But we're dealing with real experimental data here. So it's not going to be perfect. I just for the record, what I want to do is I want to see what happens if I get a cubic. So let's first let's first write out this formula. So I have y equals ax squared, but a is 0.008. So answer to A is y equals 0.008x squared. 3 decimal places is good. Plus bx, but b is 0.5398. So this actually gets rounded up to 0.540. You need to have all 3 decimals for that. Plus 0.540x minus 10.449, and we don't have to round up because that next digit is 4. So minus 10.449. That's the answer to A. A lot of work doing that. So let's see if we use Linwretch like we used yesterday instead of quadratic. So I can go stat, calc, Linwretch, enter, L1, comma, L2, comma. Now I'm going to say vars, y vars, enter, and instead of putting it in y1, I'm going to put it into y2, enter. I'm going to calculate, I'm going to hit enter again. So we're noticing that, yeah, we do get an equation that can be found from the trends. When we look at our r squared value, it's a little bit lower. Okay, it's not quite as a good fit because our r squared value, instead of being 9.1, is going to be 9.0. Now it's still pretty good, but our quadrej actually deals with it a little bit better, or kind of approximates the data a little bit better. So I'm going to go into my y. I'm just going to clear my y2. My y1, that's where my quadratic is, and I'm going to see a graph of this thing. Okay, so I need to change my settings, my window settings, and I'm going to put my y min at, it will never go before, because we're looking at our speed, it's never going to be negative. So I'm going to put that at 0. And the highest I think we did was, oh, clear, 0. And the highest I think we did was like 112. So if I go up to 150, that should be okay. My y min is, oh, actually, we didn't go up to 150, but 150 is fine for my upper bound. My y min, my stopping distance will never be less than 0 and will never be greater. Let's do 150 again too. So let's see this graph. Oh, look at that data. And look at that curve that goes right through that data. Beautiful. Now, let's analyze what's going on here. So in B, it says use your equations to compare the stopping distance at 30 kilometers an hour and 50. Now we notice that speed, okay, speed is given as our independent. Okay, so we're given our independent and we want our dependent. So use second, trace, and then value. And we're going to say x equals 30, and we're also going to find out when x equals 50. So that means when we are going 30 kilometers an hour, we're going to find out what our stopping distance is. So second, trace, value, and our x is 30. And it says right here that our stopping distance will be 13.203. So y equals 13.203, and that's in meters. So that's how much we need to safely stop or come to a complete stop. Now if we're going 50 kilometers an hour, just under double, we're going to say y equals, and let's see. So so second, trace, value, x equals 50 kilometers an hour, and we have 37.256. So 37.256 meters. Now let's analyze this for a little bit. This is less than double, okay, 30 is less than double of 60, but the stopping distance needed is more than double. So we know that it's not necessarily a linear relationship, because if it was a linear relationship, it would go up proportionally. Last but not least, determine the maximum speed that a car should be traveling in order to stop within 4 meters. The average, this should be the average length of a car. Which makes sense, because if we need to stop within a safe distance, let's see how long that takes, or what speed we should be going. So here we are given our dependent, and we want, so we're given our stopping distance and we want our speed. So we are going to use y2 equals the value, so 4, and intersect. So I'm going to go to my graph. I'm going to say y2, burp, 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 burp. y2 equals 4. I'm going to graph that. If I wanted to zoom in, I could, but I'm going to go second, trace, intersect, enter. First curve, yep. Second curve, yep. And hit enter again. So when y equals 4, our intersection point here isn't super clear. So what I'm going to do is I'm going to just zoom in to see if we can see that a little bit better. So I'm going to redo that intersect. Enter, enter, enter. That's not much better now, there is it? So I'm going to go zoom in again. I'm just going to go zoom standard, because then that gets everything out of the way. But then I can't see my my intersect here, so I'm going to go to my y. I'm going to go maybe make this up, or my x, maybe make this up to 60. Grab that. Woohoo! I see that intersection. So do you see what a dog's breakfast this can be a little bit? So I'm going to go second, trace, intersect, enter, enter, enter. There we go. Now that's what I'm talking about. So it's going to be x equals 20.387. So x equals 20.387. Just let me move. Yeah, perfect. Kilometers per hour. So we will need to be going 20.387 kilometers an hour in order for us to have a 4-meter stopping distance.